So, before we complete this session on automorphism, I want to do some more problems. The first problem we are going to attempt today is let F be any field and alpha be algebraic over F of degree n. Then how many isomorphisms can we have from F alpha to a subfield of F closure. F can be any field, like this is our F and this is our F closure and there is an alpha here. It is algebraic over F of degree n. So this is our F alpha. So I am trying to define isomorphisms from F alpha to a subfield of F closure. How many of such isomorphism can we have? For example, if you have this is equal to Q and this is equal to C and this is equal to root 2, I am talking about Q root 2. How many isomorphism can we have onto a subfield of F closure? So, given that degree of alpha comma F is equal to n, there exists an irreducible polynomial. There is an irreducible polynomial, say p of x equal to irreducible polynomial of alpha over F of degree n in F of x such that alpha is a 0 of p of x. Since the degree of p of x is equal to n, there exists at most n zeros for p of x. And each of these zeros are conjugates of alpha. For example, here reducible polynomial of root 2 over q is equal to x square minus 2. So there are two zeros for this. N is equal to 2 here. The zeros are root 2 and minus root 2. So if you are going to define an isomorphism from F alpha, this alpha should map to one of its conjugate. And for each pair of conjugate, there exists only one isomorphism. So, each isomorphism from F alpha to a subfield of F should map alpha to its one of its conjugate, and for each pair of conjugates, there exists only one isomorphism, one such isomorphism. And the maximum number of such pairs is n. So, the maximum number of isomorphism from F alpha to a subfield of F closure is n. Or in other words, you can say there are at most n such isomorphisms from F alpha to the subfield of F closure. Here actually what is happening here is we are talking about the isomorphism from Q root 2 to Q of minus root 2. And there are two. One is the identity isomorphism and another one is the conjugate isomorphism. And the degree is 2, so there can be only 2 of them. You cannot have more than that. Now we'll do another one. Let E be algebraic over F, and sigma be an automorphism on E leaving F fixed, and let alpha belongs to E. Example is going to take it as Q and Q root 2. Q root 2 is algebraic over Q. This is our E, this is our F. And root 2 belongs to Q. Then let irreducible polynomial of alpha comma F be equal to P of x. Here the P of x is going to be x square minus 2. Then and of degree n. So what are the zeros of this? Root 2 and minus root 2. These are the zeros of the irreducible polynomial. Now, sigma is an automorphism. So, sigma of alpha is equal to beta whenever alpha is a conjugate or beta is a conjugate. Beta is a conjugate of alpha. Right? So, let alpha 1, alpha 2 dash dash alpha n be the zeros of let us say distinct zeros of be the distinct zeros of the distinct zeros of p of x. Then what happens here? You can write it as alpha of sigma of alpha 1, sigma of alpha 2 dash 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 sigma of alpha n. Right? This will be probably sigma of I1 1 1 is equal to sigma of 2 1, sorry, alpha of 2 is 2 1, etc. This is alpha of n1, where these are actually one of these. For example, here either if it is not a identity map, if it's a conjugate map, then alpha of root 2 is equal to minus root 2, alpha of minus root 2 is equal to root 2. These are the assignments of a non-identity automorphism. If it's an identity, then it will be root 2 and minus root 2. And this implies sigma induces a permutation on the set of zeros of the irreducible polynomial over f. What do you mean by permutation? See, if you take a set S is equal to 1, 2, a permutation will be 1, 1 and 1, 2. Or another, 1, 1 and 2, 2. Or another permutation will be 1, 2, 2, 1. That is how you do it, right? It's actually, you normally write it as 1, 2, 2, 1 or 1, 2, 1, 2. So these are the zeros of the irreducible polynomial. And if we are mapping 1 to 2 and 2 to 1. So that is one sigma. Here this is identity map 1 to 1, 2 to 1. So this is another automorphism. So each automorphism induces a permutation on the set of zeros. The set of zeros are alpha 1, alpha 2 dash dash alpha n. So it will be something like this: alpha 1, alpha 2 dash dash alpha n, alpha 1 1, alpha 2 1 dash 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 alpha n1. These are actually same as this in a different order. That is how you define the permutation. So the result is any automorphism on E induces a permutation on the set of zeros of the irreducible polynomial alpha when alpha is algebraic. Of course, E is algebraic means alpha is algebraic. I will do another problem. Let E be algebraic over F and S is equal to sigma I belongs to I, be a collection of automorphisms on E leaving F fixed. This is not the complete collection of all automorphisms that leaves F fixed. It's a sub-collection of this. The whole collection we normally denoted as G of E over F. So S is actually a subset of this. That is, you can say S is a subset of G of E over F. Now, if S generates a subgroup H of G over F, then what is the relation of ES and EH? This is actually the fixed field of E over S, the fixed field of E over H. Give you an example here. Let this be Q of root 2 comma root 3, and this is our Q. This is our E and this is our F. When you know that the group of E over F here is 1 comma psi of root 2 comma minus root 2, psi of root 3 comma minus root 3, and psi of I will write it down here. It's going to be G of E over F is equal to, first item is the identity map, then psi of root 2 comma minus root 2, psi of root 3 comma minus root 3, and psi of root 2 comma minus root 2 after psi of root 3 comma minus root 3. This is our whole group. but I'm taking a sub-collection of this. So my S is actually psi of root 2 comma minus root 2. That's it. That's what I'm saying here. And this generates, actually, if you say psi of root 2 comma minus 2 square is equal to I. So the group generated by S is equal to I comma root 2 comma minus root 2. That is what I am trying to say here. Here, this is our H. Sorry, this is our this is our S, and our H is I comma psi root 2 comma minus root 2. Our S is this, our H is this. So what we need to do is we need to find out the relation between E of S and E of H. This generates H. So let us see what happens. S generates H. So it's definitely a subset of H. S generates H. That implies E of H is contained in E of S, because this has got lesser number of automorphisms than this. So the fixed field will be the other way. This is actually, what is the meaning of this? The elements from E that are fixed by elements from H. So H is smaller than H, or subset of H. S is subset of H. So E of H is a subgroup of, a subfield of E of S. So this is one relation. So can we have on the other side? So let us take an example here. Let X belongs to E of S. What does that mean? This means that X belongs to this means that sigma I of X is equal to X for all sigma i's in S. That is the definition of this, right? This contains all the elements from E that are fixed by elements from S. So when you say S generates H, that means any power of sigma i's belongs to H. So from here, sigma I of X is equal to X implies X is equal to sigma I inverse of X for all sigma i's in S. And also sigma I to the power of n of X, this means sigma I of sigma I of sigma I of sigma I n times. That is also equal to X, because it is not moving X for all X belongs to, for all and for all sigma I belongs to S. What does that mean? Where are these sigma i's to the power of n and minus 1? They are all in H. H contains all powers of products of elements from S, because S generates H, and that implies sigma I of x equal to x for all sigma i's in H, and that implies x belongs to E of H. What does that mean? We started off with x and ended here x belongs to E of H. That means I want to go back here. E of S is a subfield of E of H. But we know that E of H is a subfield of E of S, so that implies EH is equal to ES. Coming back to our example here, what I am trying to say here is what is E of S? E is actually Q root 2 comma root 3 of S. S is just our sigma of root 2 comma minus root 2. And what is E of H? Q of root 2 comma root 3. This is actually going to be I comma psi of root 2 comma root 2. These are equal. That's what you are saying. We can compute this one. I'm not going to do it here. We can compute the elements of Q root 2 of root 3 on this and here, and we'll see that they are equal. Do it in exercise. We'll complete this chapter on automorphism on a field with one more problem. Let phi p of x equal to x to the power of p minus 1 plus x to the power of p minus 2 plus dash 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 x plus dash 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 plus 1 be in Q of x, where p is a prime. Then QP of x is irreducible over Q. Now let psi be a 0 of QP of x. Then our question is, what are the other zeros of QP of x? There should be p minus 1 elements. Doesn't need to be distinct, and we are going to show that it's distinct. There are p minus 1 distinct zeros of QP of x. If one of them is given, then what are the zeros of the other? What are the other zeros of phi of p? This phi of p of x can be written as x to the power of p minus 1 by x minus 1. For example, x cube minus 1 divided by x minus 1, this actually can be written as plus 0 x square plus 0 x plus 1 minus 1. So you can divide this one as x square x cube minus x square plus 0 x plus x square minus x minus 1 plus 1. That's what this one is. Here our p is 3, a prime number. Now let psi is not equal to 1. I am actually assuming that psi is not equal to 1. Okay, psi is not equal to 1 because if psi is equal to 1, this cannot be 0. So psi is not equal to 1. So what does that mean? That means that implies z to the power of psi to the power of p is equal to 1. If psi is not equal to 1 and zp of x psi is equal to 0, then psi to the power of p minus 1 equal to 0, that means psi of p is equal to 1. Now let us take psi of I to the power of p, where I is greater than 0 and less than p. If it is equal to p, then it's automatically 1. So I'm going to assume that it's less than p. So what does this mean? So psi of I to the power of p is equal to psi of p to the power of I, and that's equal to 1 to the power of I is equal to I. That means psi of I is a 0 of psi p of x, where 0 I is greater than 0, less than p. Okay. Now let us show that these are distinct. So let tau of j is equal to tau of I, and that implies tau of j minus I is equal to 1. This is not possible because the lowest power of tau that needs to be 1 is p. This is not possible because j minus I is less than p. That means that if psi is a 0 of qp of x, then psi square dash dash psi p minus 1 are also zeros of, are the distinct zeros of, are the distinct zeros of qp of x. We want to do one more property of the group of the field. I want to see what kind of group is G of Q of psi over Q. This is actually the collection of all automorphisms on Q of tau, Q of psi over Q. So this is equal to automorphisms on Q of psi that leaves Q fixed. Now let us take two elements from here. Sigma 1, sigma 2 belongs to G of Q of tau over Q. Now, psi 1 of after psi 2 of tau is equal to, tau is a, psi is a is algebraic over Q. So this should actually map to a conjugate of this. So this will be sigma 1 of psi of I for some I. For some I. Because sigma 2 should map to psi's conjugate, and psi's conjugates are psi 1, psi 2, psi 2 power 1, 2, 3, it's up to p minus 1, and that is equal to psi of j and I to the power of j. This will be psi of I to the power of j for some j. Because again, for the same reason, psi of I should map to one of its conjugate, and that is equal to psi of ij, and that is equal to psi of ji, and that is equal to sigma 2 of after sigma 1 of we started from sigma 1 after sigma 2 of tau is equal to sigma 2 after sigma 1 of tau. That means this is abelian. Q of psi over Q is